When George Carlin's high school science teacher said that entropy effectively meant that all systems would eventually break down, he thought to himself, what a wonderful thing! Perhaps I can contribute to this process in some way. And today, it's our turn to have a go. Any spontaneous process will lead to an increase in the entropy of the universe, so even something as mundane as brewing tea could in theory demonstrate it. I wouldn't make tea this way, but with a little thought, it does become clear that the entropy of the soluble material in the tea, and any sugar that you need to add, will increase as they dissolve. Meanwhile, the entropy of the surroundings must increase as the drink begins to cool. So given that I could choose anything to demonstrate entropy in action, I like to have something that students aren't likely to have met before. And that's where the Marangoni effect can come in. One droplet of coloured liquid placed upon oil seems to explode into many smaller ones in endlessly fascinating patterns. While this effect can in principle work with ethanol water mixtures, and this is in fact the explanation for wine legs or tears of wine, I like to use water mixed with isopropanol, also known as propan-2-ol. The movement is driven by the lower surface tension in the alcohol, so the greater the alcohol proportion, the faster the flow. Around 40% works well, so I add 4 centimeter cubed of isopropanol to a 10 centimeter cube measuring cylinder and then fill to the top mark with water. I have a stash of concentrated food dyes from another demonstration to show intermolecular forces, but ink should work well too. Simply cover the base of a plate or shallow tray to a few millimeters with vegetable oil, and then place a few drops of your alcohol mix on the surface and wait. A webcam can really help here. Evaporation is important here, and that means that if you're in a really hot lab, you might need to tweak your proportions. Too much water in the mix and your drop will remain as a bead. The surface tension is too high and a little bit more alcohol is required. If the droplet spreads too far and wide, then you need more water. Get it just right, and the effect can be mesmerizing. It's tempting to think of one droplet bursting into many as being associated with an increase in disorder. But really, we're less interested in the tens or hundreds of droplets and more interested in the 10 to the 20 molecules of alcohol evaporating into the surroundings with their myriad ways of arranging quanta of energy. The whole process is kicked off by these evaporating alcohol molecules. They evaporate faster than water because of their reduced ability to hydrogen bond, and if the surface tension of the droplet is low enough that it flattens out, then these alcohol molecules won't be replenished at the edge of the droplet as quickly as they can be nearer the center. It just takes longer for them to diffuse out there. Now that the surface tension in the liquid at the edge has begun to increase with the higher proportion of water molecules, this area tends to draw liquid along the surface towards it. Beads gather at the edge of the liquid as it seeks to minimize its surface area, and we're left with a galaxy of tiny droplets. This effect was one that Willard Gibbs explained in the same paper in which he developed the equations your students might just about to be introduced to, but there's no need to read hundreds of pages of thermodynamics in order to understand it. Better just to play with and appreciate this tiny little masterpiece, so give it a try.